Thank you. And yeah, so this is joint work with Rahul Santhanam, who's at the University of Oxford. And yeah, I'm going to tell you how to construct deterministically random strings. So the motivating question in this work is essentially the following. Should every non-constructive existence argument have a corresponding efficient explicit construction? So more concretely, throughout TCS, we have all these examples of pseudorandom properties of objects where we have a non-constructive argument that shows that they exist. And we want to match these with polynomial time explicit constructions. So for example, rigid matrices, counting argument shows they exist, and it's open in many parameter settings to give some efficient algorithm that can actually deterministically output one example of such an object. And sort of common informal wisdom here is that in each specific case of this type of problem, once we just advance our understanding of the relevant pseudorandom property enough, probably we should be able to come up with an example. And sort of there's many historical cases where this has happened with expander graphs, extractors, error correcting codes, etc. But what we're looking for in this work is kind of a structured complexity theoretic answer to this question. So under some well-believed complexity conjecture, should there be sort of a universal way to make non-constructive arguments explicit for these type of problems? So to understand this problem, we need to introduce a search problem called the range avoidance problem. So this is a search problem introduced in joint work with Kleinberg, Mitropolsky, and Papadimitriou, where the input to the problem is a Boolean circuit that stretches its input from n-1 bits to n. And the goal is to find some n-bit string that's outside the range of the circuit. And we call it a void for short. And so in previous work, it was shown that most explicit construction problems we care about can be reduced in polynomial time to this range avoidance problem. In particular, all the ones that I showed you on the last slide. So this gives the first potential avenue we could have to addressing this main question, which is that if we could show that this range avoidance problem is in general solvable in polynomial time, we would get a positive answer to this main question one. But unfortunately, this was kind of ruled out essentially in work from a few years ago by Ilongo, Lee, and Williams, where they showed that under plausible cryptographic assumptions, there probably is not, or there is not under these assumptions, a polynomial time algorithm that can in general solve this range avoidance problem. So we're back kind of to square one. But something about this result is that it does not imply the hardness of problems that are of the form of explicit construction problems. It's really a contrived example of the range avoidance problem. And so it still doesn't give us really a negative answer to our main question. It just says that we can't approach it by generically solving range avoidance. So how can we sort of differentiate explicit construction problems from general instances of range avoidance? Well, an observation from Ren, Santhanam, and Wang is that for explicit construction problems reducible to range avoidance, there's sort of a normal form complete problem here that it suffices to solve, which is given 1 to the n as input, so just the length of something. The goal is to output a string of that length whose time-bounded Kolmogorov complexity is n, meaning that it can't be produced by any machine of length strictly less than n. And really, this is a family of problems indexed by some polynomial time-bound. And yeah, in many slides, I'm going to talk about constructing k-poly random strings. What I mean is fix any polynomial you want, and the goal is to output a string that's k-poly random for that specific time bound. So this is the problem that we want to solve, and if we can sort of positively solve this under some assumption, then we'll get positive answer to all these explicit construction problems. And something to note also is that for most specific explicit construction problems we care about, we don't actually need the compressibility, the Kolmogorov randomness, to be all the way up to n. It's many times sufficient to get something close to n, up to some polylog factor, or even maybe n to the low of 1 factor. In other cases, we need to get something like n minus n to the epsilon. But we don't really, yeah, so there's this other parameter, which you might call the stretch or compressibility factor, which we don't need to be all the way up to n. And so our main result is that under some plausible, we think, hardness assumption, which is similar to the assumptions that were talked about in the last talk, and I'll say a little more in a second, there are efficient algorithms that can do precisely this task. And specifically, we can produce k-poly random strings that have this n over some polylog, or maybe n over some even smaller growing function of n incompressibility. So there's going to be various versions of this depending on some specifics of what this assumption looks like. So in general, what the assumption is that there's a problem solvable in time t of n that is hard for algorithms with an NP oracle that run in some polynomially smaller amount of time and using 2 to the epsilon n bits of advice, which is polynomially smaller than like hard coding the truth table, which you could then solve the problem trivially. So assumptions like this were talked about in the previous talk and have been made like very commonly throughout the sort of hardness randomness literature. But the main sort of distinction for us is that we're going to need to make these assumptions when the time-bound t is very, very large. So sort of all our main results start to kick in when we have it like doubly exponential, and then we're going to get like stronger results if we assume it for like triply, quadruply exponential, et cetera. So this is the non-standardness of our assumption, that we need to push the time-bound larger. And so like the typical regime of like the Impaliato-Wigderson theorem, like typical de-randomization regime is that this t of n term, like, sorry, the t of n to the epsilon term, which is like the runtime of the algorithms that we need hardness against, is something like 2 to some small constant times n. So that's the comparison we're making. We need to be kind of exponentially larger at least than that. But one prior work to note that also involved kind of taking these standard assumptions and pushing the time bound beyond their usual regime is in the subject of superfast de-randomization, where Chen and Tell used sort of assumptions of this form where we start with a standard one and push the time bound a little further to design some like very fast de-randomization algorithms. And in their case, they needed hardness against algorithms that were running in like 2 to some large constant times n. So I'll mention some other connection to this work also, but like this is kind of an inspiration for using assumptions of this form. So yes, this is what our general results look like. And there's sort of, when we adjust the assumptions at the top, we'll get different versions of the bottom. So I'll tell you one like very concrete version is that if we assume that there's a problem in doubly exponential time, which cannot be solved like polynomially slower with an NP oracle and 2 to the epsilon n bits of advice, under this assumption, we're going to get a quasi-polynomial time algorithm that can produce k-poly random strings that are like n over polylog n random. So this is one instantiation. And like using this in the connection to these explicit construction problems, we can say that like under this assumption, first of all, we get that exp requires very, very close to maximum circuit complexity. So 2 to the n over poly n. You can think of this as like, this is the same as saying there's a quasi-polynomial time explicit construction of a very, very hard truth table. And we get various other explicit constructions like rigid matrices that we can print in quasi-polynomial time that have very, very close to valiant rigidity parameters. And the other one, I'm going to be a bit more vague about what I say by stronger assumptions. We're going to need to increase the time bounds and also change slightly the qualitative form of the assumption. But under stronger assumptions, we're going to be able to get, first of all, polynomial time constructions instead of quasi-polynomial. And also, we're going to be able to shave off, instead of like compressibility n over polylog n, we're going to get n over any fixed number of logs that you want. So yes. And in this regime, we're going to be able to get like valiant rigidity, full valiant rigidity, and polynomial time, various other explicit constructions from this under the stated hardness assumption. Yep. Yeah.
What is the question that it seems like self-contradictory? Keep creating strings that have high complexity using a
Yeah, sorry. So this is where I'm like hiding quantifiers in a way that is maybe confusing, but I didn't want to clutter the page with some. So when I say k-poly random strings, what I mean is for any fixed polynomial, n to 100, I can construct strings that are n to the 100 random by an algorithm that runs in a larger polynomial depth, so like n to the billion. So does that make sense? Yeah, okay. So now I'll tell you about the approach that we're going to do, that we're going to use to solve this, which is very simple. So like the key ingredient we're going to need is to design a PRG for p to the np with doubly logarithmic seed length, or perhaps smaller. And again, so I'm going to be hiding quantifiers here. When I say p to the np, what I mean is we want to design a PRG that fools time, n to the 10 with an NP oracle. I'll say that later too, but yeah. So I'll tell you how we're going to use this first to solve the problem that we're looking at, and then I'll tell you how we approach doing this. So just to recap, what does this mean? So we have some constant c. We want to fool time NP algorithms that run in n to the c time. And what we're designing is a generator that's stretching O of log n bits to n bits. On the one hand, we want it to be efficiently computable, like quasi-polynomial or polynomial time. And on the other hand, we want that for every fixed language in this complexity class, the probability of random strings in the language is approximately the probability that a random output of the generator is. And the error that we need, we're just going to need some constant error. We'll be happy with that. And so how are we going to use this? Well, the idea is we're going to consider the test, which tests whether a string has high time-bounded Kolmogorov complexity. So this test is going to be satisfied by a random string with probability 1/2, at least 1/2. And it's testable with an NP oracle. This is the key property. So the idea is if I had one of these pseudo-random generators, I know that a random string has high time-bounded Kolmogorov complexity. Therefore, about half or a constant fraction of the strings in the range of this generator will. And so if I enumerate all the strings in the range of this generator, because it's doubly logarithmic, the number of strings is polylogarithmic, right? And so I'm going to end up with a list of sort of candidate incompressible strings of length only polylog n. And what am I going to do with that? So what I just said is we design this PRG, I enumerate all its outputs, and I obtain a list of polylog n many n-bit strings, so that at least one string in this list has like basically maximum time-bounded Kolmogorov complexity. And then I'm just going to do this very dumb thing of just concatenating these strings together. The idea is now I'll obtain a string of length m, where m is like n times polylog n. And you can show very easily that the time-bounded Kolmogorov complexity, maybe the time bound that it's hard against decays very slightly, and the Kolmogorov complexity decays by some additive logarithmic thing. But otherwise, it's basically the Kolmogorov complexity of the concatenated string is basically n. And as a function of the length of the new string, that's like m over polylog m. So this is the basic idea. Does that make sense? So this is our strategy. And all that's left is to do the top thing. Yep. So just to recap a bit is that like the standard hardness randomness paradigm tells us that we can do this. We can design PRGs for time-bounded NP oracle circuits or NP oracle functions with logarithmic seed length, and this under some like standard assumptions that we mentioned before. This construction actually fools P to the NP / poly, so polynomial size non-deterministic circuits. And it's well known that like if this is what you want to fool, this is the class of tests you want to fool, you need to have logarithmic seed length. But like it's only because you're trying to fool P to the NP algorithms with advice, with polynomial advice. So this is like the key observation is that if we don't need to fool algorithms with advice, then at least information theoretically, this should be achievable just with any super constant seed length. And the reason that we don't need to fool algorithms with advice, if you remember, we're only trying to fool a single test, which is the test whether a string has high time-bounded Kolmogorov complexity. So this is not, this test does not involve any advice. It's like one fixed test for all n, and we only want to fool this one test. Yeah, SAT. Yeah, you could. Yeah, some fixed NP complete language. Does that make sense? Like any fixed NP language. Yeah. And that's just it's just used to test if the string has high Kolmogorov complexity. Yeah. Like, does there exist a program? Cool. And yeah, just to say, this is the like another like major similarity with this Chen and Tell result in superfast de-randomization is that like one of the key observations at the start of this work is to see that like when you want to fool algorithms that run in some large time bound but with small advice, you only need sort of the seed length to scale as some certain function of the advice complexity, not the time complexity of the algorithm. Cool. So how are we going to construct this? The idea is like very simple, and I'll be able to explain it in a couple of slides. So initially using like a standard hardness randomness framework, I'm going to have at the top like n-bit strings, and I'm trying to fool some language, L, I'm putting at the top, which reads n-bit strings and outputs a bit. And we know under like one application of a hardness randomness paradigm that I can construct some generator which will have a O of log n seed length and fool it with some constant error epsilon. So it'll fool that language L. And the idea now is that I just want to view, the input length, these seeds as some new input length of a new test, and plug in, another pseudorandom generator whose seed length is logarithmic in this output length. And the claim is that if the outer generator fools whatever complexity class the language L is, and if this inner generator can fool algorithms that run in sufficient resources to sort of simulate both one application of the top generator plus deciding the language L, then you'll automatically get that the composition of these two generators will fool, with 2 epsilon error, will fool the original language L. So it's like a standard argument in, pseudorandomness, that like the composition of pseudorandom generators is also a pseudorandom generator. So this is kind of what we want to do. And now we just need to think about, okay, I can do this top thing under the standard hardness randomness paradigm. Like, what do I want to plug in here to reduce the seed length again by another logarithmic factor? And so the idea is, for the top one, we're going to plug in the hardness randomness paradigm, where we take some the Impagliazzo-Wigderson generator that takes as input a hard function. When we plug in that hard function, we get a pseudorandom generator. And the properties of that hard function we need is that its length is like the input length of the function is like logarithmic in the output length of that generator. And it's hard for algorithms that run in time exponential in the input length. And now, if you think about, so now I imagine I have sort of strings of this length. And in order to fool the top level language, I want to fool the test that applies the outer generator and then runs the test L, right? And so the idea is that that test is going to run in time. By assumption, I could construct G0 to run in time polynomial in like the outermost n. And so as a function of this input length, that test is going to run in time like exponential in the input length n1. And so what I now need to do is define like a generator sort of at this input length, which is going to fool NP Oracle algorithms now running in exponential time. And if I kind of run through the standard hardness randomness paradigm again and sort of relativize everything to an exponentially larger time bound, you'll see that what you need is to produce now a truth table, which is computable in like doubly exponential time in terms of its input length, and is hard against like correspondingly like polynomially smaller circuits. Right, so this is the general idea. And sort of with some caveats I'll say in a moment, we can just continue this any constant number of times, and sort of we need to assume our hardness for correspondingly larger and larger time bounds. And we can reduce the seed length down to some like arbitrary log n. So this is the basic idea of the construction. There are a few technical issues that I'm brushing over. So first thing is that because sort of these very large like tower exponential time bounds exhibit some annoying behavior, like if I have the input and I change it by a constant factor, I'll change the overall value by like a super polynomial amount. And so for this reason, like we either in various cases need to sacrifice the runtime from being polynomial to quasi-polynomial or quasi-polynomial, et cetera, or we need to sort of do a bunch of tricks to using like time constructible. So we need to make our hardness assumption for all time constructible bounds, where the time bound is not like 2 to the 2 to the n. It's some machine that it's some arbitrary time constructible round, and we need to like play some kind of annoying tricks with it to get this to work. So this I'm brushing under the rug. The more interesting thing I'm brushing under the rug here is that when we go below doubly logarithmic seed length, we actually need to make assumptions about the Kolmogorov complexity of the input length n itself. So when we do this construction to achieve like a S of n seed length, we need the Kolmogorov complexity of the number n. So really this should be like k poly of n is at most about exponential in the seed length that we're trying to achieve. So this is no issue when the seed length is like O of log n, because the number n always has Kolmogorov complexity like log n. But when we push down a smaller seed length, we can only do it for n that are like input lengths n that are highly compressible. So for example, if input length n is itself like a tower of 2s of some height, then we can do it for those n and not others. And I have enough time to say really briefly why this comes up is that if you imagine I'm at this input length reasoning about what is the language of like seeds that when I run them through the generator fool this or that language, you'll realize that to reference this entire construction, all of it's defined as a function of the outermost n. And so I'm going to need to fool algorithms that have enough advice to encode the number n such that they can describe the construction. If the number n is compressible enough, then we can do this. Great. And the final thing I want to mention is that there's also like a seed length lower bound that we prove that it's so any sufficient, I'm waving my hands a lot about what I mean by black box here, but any sufficiently black box construction, like a black box hardness to randomness construction of a PRG that only uses a constant number of hardness assumptions, I'll say what I mean in a second, requires the seed length to be some iterated logarithm of n. When I say using constantly many hardness assumptions, I mean like in this construction here, you look at like whatever n is independent of n. If I chose d to be a constant, I'm only sort of using a hardness assumption for a constant number of functions on a constant number of input lengths. Like I have the f0, f1 up to fd. And sort of it's provably necessary that if you do this, then actually it'll be the same O of 1. That's the best seed length that you can obtain. And what this follows from is like viewing this, our main construction, as a kind of a reconstructive extractor for multi-source, for CG sources with a seed. Sort of along the same lines as like how Trebison's famous result that interprets like the standard hardness randomness paradigm, if you're familiar with this, as like a reconstructive single source extractor. And then we prove just that like any CG source extractor of this form, however you choose the lengths of the sources, you need to have like iterated logarithmic additional seed. Great. That concludes everything. And I just want to mention 2 open problems. So the first one, maybe the main problem is, can you construct random strings under like a simpler form of hardness assumption? In particular, it's not clear to us at all that you should need assumptions that involve these like really large time bounds. And the second one is, can you construct omega n like random strings? So without these log factors. I mean, or even stronger, n minus square root n be even more interesting. And we don't know any of our these.